I don't know about you, but there are certain things in astronomy that I find very interesting, but also unanswered. I've been teaching astronomy to students for perhaps 4 decades, on and off. Elementary school all the way up to university and postgraduate. And one of the questions that is answered quite often is, how do planets form? And you know, for me, it's a bit of a disappointment, because when you go to a standard textbook, there's a standard textbook here, and you open it up, there's always a chapter about planetary formation, and there's lovely little drawings and pictures and the like, you know, and the explanations are wanting. They're, you know, lovely drawings. They talk about nebular theory, they talk about Immanuel Kant, and then they sometimes give you nice clues. Here's some clues. The orbital planes of the planets in our solar system are nearly the same and lie almost in the equatorial plane of the Sun. The planets all orbit the Sun in the same direction, and most planets rotate in the same direction that they revolve around the Sun. Planetary orbits are almost circular. Even Mercury's orbit about the Sun varies about 21% from circularity. In a few minutes, we'll talk about that, actually. The regular satellite systems of the outer planets mimic the solar system and the characteristics listed above. The Sun has more than 99% of the mass of the solar system, but less than 1% of the angular momentum. In other words, the Sun rotates much too slowly to have an angular momentum comparable to that which is contained in the orbital motions of the planets. Now, these are just descriptive statements. And when you talk with professional astronomers, they still have not come up with a definitive model of how it is possible for solar systems and exoplanetary systems to form. But I've had a bit of fun in the last few years, and I've come up with 2 models, one of which relates to something we've known since the 17th century, the bifurcation model, and the other is a 2-parameter turbulence model that allows us to find fundamental differences, or distances, I should say, in planetary systems based on 2 things, 2 parameters. One is the radius of the central star, and the other is the choice of a Reynolds number, and therefore, as you suspect, some turbulent behavior. This little video that I will share with you today is a look at my model that perhaps explains what we see in both our solar system and in some exoplanetary systems. In 1734, Emanuel Swedenborg of Sweden and 1755 Immanuel Kant of Prussia presented theories of nebular planetary formation. In 1943, Carl von Weizsäcker came up with his theory that was presented in a Zeitschrift für Physik paper. It's in German, not well read and received, and it was made known to the world by George Gamow in 1945, and it becomes the standard description of what happens in nebular planetary formation. Here's a short video that was put together by NASA about the evolution of a planetary system. And of course, the whole idea here is we start with a flat nebula that evolves into the planets. Now, the big question is, how does it get to that shape to begin with, and how does the spacing form between the planets? And this is what I'm going to try to explain in a few minutes. For the next half of this video, I'm going to walk you through 2 things. One is a bifurcation model, which, if you look closely, is very similar to the Boe-Titius law. I'll give you an explanation of, for instance, the fundamental distance, or the basic distance. In the Titius-Bode law, it's always a geometric progression. And in the second presentation, which is about the turbulent model, you'll see why it's a bifurcation function, because it relates to turbulent flow. And in this model, I'll be able to tie the bifurcation and the turbulent model together and apply it not only as a descriptor of our solar system, but a descriptor to other exoplanetary systems, beginning with G-type stars. Now, if you look closely and listen closely to what I'm about to present to you, you'll see that there is ample empirical evidence to suggest similar formation in other exoplanetary systems. But you'll also notice the relationship between Reynolds number and the spacing of planets in these exoplanetary systems. In our solar system, we have terrestrial planets, we have gas giants, we also have an intermediary state, which we call the asteroid belt. But we are seeing essentially three groupings based on Reynolds numbers. For Mercury, for instance, you'll see a Reynolds number 3500 will provide you the distance Mercury is from the Sun. And I want to explain something to you as I go through this particular explanation, that I chose the Reynolds number and then found what distance it provided in my model. So I chose the Reynolds number 3500, which is pyroclastic flow, and this gave me the distance of Mercury from the Sun. I chose a particular Reynolds number for the gas giant based on the onset of turbulence for a specific type of configuration, a Venturi effect, and this in turn gave me exactly the distance of Jupiter from the Sun. And then I looked at relationship between density and Reynolds number, and then based on the Reynolds number I'd chosen for Mercury and for Jupiter, and based on the density expected for a ice body, I ended up determining a Reynolds number, and when I put that Reynolds number into the model, out came the distance of Ceres from the Sun. As you look closely at the implications of the two models, you realize that it not only is a very good explanation of our solar system, but when you look at some exoplanetary systems and apply the model there as well, you get the spacing as seen in exoplanetary systems. And I've started essentially with G-type stars, but it turns out as you expand the model into K-star type stars and whatever, you find that it's still a very good representation of what you see. So this is actually the purpose for this video. I apologize for the poor quality because I'm not a filmmaker. I'm an educator and I'm a scientist. I'm not a Hollywood type. But if you can bear with me and just focus on the message and not on the medium, I think you'll find something of consequence. There is, of course, the bifurcation value in the Bowes-Titius law. This is an empirical rendition that I put together based on planetary and exoplanetary data. This is the two-parameter turbulence model, and it depends the Reynolds number and the radius of the star. When you choose a Reynolds number 3500 for Mercury and put in the early star size of the Sun, you get an exact match in the Bowes-Titius law. When you go on and look at the characteristics of ice planets, you get a fit with the asteroids, and when you look at the gas giants, Reynolds number 40,000, you get exactly the orbit of Jupiter on the Sun. What the Hubble telescope has allowed us to do is to look at exoplanetary systems like the Trappist 7 system, which has been studied quite closely, and people have tried to understand why it is you have so many planets so close to a small M-star size star, a red dwarf. It turns out if you actually put in the pyroclastic number 3500 for the Trappist system, you get exactly the distance of the furthest planet in the Trappist 7 system. It appears that this material stalled within that distance, formed a pancake, and then evolved through gravitational resonances into the planets themselves.